Hi there, this is Richard Walker from Lucidate. Welcome to this fourth video in Lucidate's series on ensemble methods. The previous video compared three machine learning models: decision trees, random forests, and AdaBoost. Random forests and AdaBoost are both examples of ensemble methods themselves. We use these approaches to create a diverse set of uncorrelated models. When combined, the output of multiple models outperforms single models nearly all of the time. For random forests and AdaBoost, we generated diversified models by shuffling the dataset or by selecting records from our training set that our models had previously struggled to correctly classify. This combination of random shuffling and forcing the models to be trained on data that is challenging yields increased model performance. In this video, we're going to discuss stacking. This is yet another ensemble technique. Stacking involves training a whole array of different AI models on the same training data and then using data fusion and AI techniques to optimally combine the output of these multiple models. For classification tasks, we could simply let multiple models vote and take the majority vote as our best prediction. Frankly, there's nothing wrong with this approach, but as we shall see, we can get even better outcomes by using a further AI model to determine the best prediction. More on that in a couple of minutes. To illustrate the stacking process, we'll use our ensemble of three models from the previous video: decision trees, random forests, and AdaBoost. To these three models, we will add a further four. Firstly, K nearest neighbours. This is a technique that uses proximity clustering in high-dimensional spaces. Secondly, support vector machines. This approach finds a hyperplane that separates the data into classes. The selected hyperplane is the center line of the widest street between the data. Thirdly, neural networks. This technique attempts to fit a parameterized function between input data and output data. It uses a backpropagation technique based on gradient descent to tweak and nudge the parameters of the function to get the optimum output. This popular AI approach is modeled on the biological neurons that are part of the human brain. Finally, we'll look at logistic regression. This approach maps inputs in a multidimensional feature space onto a set of output classifications using a soft decision boundary. If you're unfamiliar with any of these techniques, then don't worry. Lucidate has explainer videos on all of them. Links are in the description. We'll first explain how the stacking process works. Then we'll work through an example on our lone default dataset. After that, we'll single out a couple of points of interest and some key concepts. So firstly, let's see how stacking works, starting with our dataset. The first thing that we will do is split this dataset into three unequal parts. 70, 20, 10 is a good starting point, but feel free to experiment and tweak this ratio should you wish. The larger dataset will be used to train our base models as usual. The middle-sized dataset will be held back from training the base models. This is data that the models have not seen during training and will be used to test these trained models and allow the base models to make predictions on out-of-sample data. Firstly, this will give us some accurate test scores for each base model: precision, recall, F1, area under curve, etc. Secondly, we will use this dataset to train a stack or aggregator model. This model will be the one that intelligently fuses the different outputs from our base classifiers to come up with a more accurate ensemble classification. And then we'll finally use this smaller held back dataset to test our trained stack model. So let's walk through this step by step. We'll take our training data and train our base models one by one. For our decision tree, we will work out our splits at each level by minimizing the Gini impurity. For our random forests, we will use bagging to shuffle our training set to generate forests of uncorrelated decision trees. For AdaBoost, we will use boosting to selectively generate training sets that are richer in data samples that previous models have struggled with. And we'll continue with this using clustering for k nearest neighbours, finding hyperplanes for our support vector machine, backpropagating to train our neural network, and tweaking our weights for our logistic regression decision boundary. Once our models have been trained using our largest data subset, we will use our out-of-sample held-back dataset to ask each of our trained models to make predictions. If the models have been trained well, then in many cases they will all make the same correct predictions. But frankly, the more interesting situation for us is shown on the screen. Here we have a wide disagreement and a split decision. We have a 4-3 vote in favour of default. A simple and frankly not terrible solution would be to take the majority vote. But can we do better? Well, a more sophisticated approach is to look at the outputs from our base models as a feature vector. This vector has 7 elements. The first, 4th and 7th elements in this case are repay. The 2nd and 3rd, 5th and 6th are default. We can use this vector as an input to an additional AI or machine learning model. We know from our training dataset what the target values or correct classifications are. The inputs to this stacked model is therefore a simple 7-element vector rather than being the full set of inputs containing things like debt to income ratio or annual income. This stack model will be trained to predict an ensemble classification based on the output classifications of each base model. Then we can use our final held out data to test how accurate the stack is. Once again, we use this data as an input to our base models for them to make predictions. These predictions are fed as a vector into our stack model to test how accurate the overall approach is. By default, logistic regression is used as the stack model, but this is just a default. You should experiment with a bunch of different models to see which gives the best aggregated classification, as we will see in a couple of minutes. We'll start with our pipeline where we left it at the end of the last video. Here we have some data wrangling, some train test splitting of our data, and our evaluation of our 3 models, the decision tree, random forest, and AdaBoost learners. Let's add the 4 additional models to this setup to create a stacked ensemble. We'll start with k nearest neighbours, then add a support vector machine, follow this with a neural network, and we'll give this network a couple of hidden layers of 10 and 6 neurons respectively. And then finally, we'll add our logistic regression model. We'll let the models run and fill out the performance metrics table. Before we add our stack aggregator, we can take a quick look at some of the metrics from the models. At first glance, it looks as though our neural network, our random forest, and our logistic regression were the best performers. As we shall see in a couple of minutes, initial appearances may be deceptive, and we'll need to do a more thorough job of looking at each model. The logistic regression has a very low AUC score of 0.591 that might give a clue as to some suspicious performance, and we'll check back on that later. But let's first create a stack. This is easy to do, just drag in a stack widget and connect the output of all of the base models as an input to the stack. If we don't specify an aggregator model for the stack, the default will be logistic regression. We'll stick with this default for now, and then add a neural network and a support vector machine later to compare performance. Once all of the base models are connected to the stack, we can then connect up the stack to our test and score module. Even on this small data set, it will take a while to run all of the models and then use their predictions to train our stack. Again, let's remind ourselves of the topology here. We have 7 base models that are being fed some held out training data. The models have not seen this data before when they were trained. Now they're seeing it afresh and making predictions. And then we're feeding these predictions into our stack for training. We're training a logistic regression model with the predictions from these base models and the known targets from our second medium-sized training sample. Let's fast forward to the results. Firstly, we'll take a look at the area under the ROC curve, which is perhaps the best single metric in isolation. In the table, we can see that the stack has the best area under the curve score of 0.693, with the neural network and random forest in second and third places. We can hook up an ROC widget to our pipeline and confirm that the best area under the curve is for our stack. A good way to look at the inner workings of the stack is to hook up a data table viewer to the output of our test and score widget. This shows the actual target variable we're trying to predict in the first column, along with the individual predictions of each of our models. Then the next set of columns shows the actual floating point output from the model classification. Values very close to 0.5 indicate that the model was unsure whether this was a defaulter or a repayer, whereas values very close to 0 or close to 1 indicate a higher confidence. This is the feature vector fed to the stack. The stack is a model of models being fed classification confidence from each of the base models rather than the raw lone default data. So let's just switch gears a little bit and, as promised, return to that murky looking logistic regression score. A big giveaway is the recall and specificity scores. This lone default dataset is unbalanced. It has approximately 80% repairs and 20% defaulters. If we look at our confusion matrix, we can instantly see what has happened. The model has simply said that every borrower will repay. Now, this gives a misleading accuracy score of 80%, but the model isn't really discriminating at all. So one thing we can do is change the regularization parameter from ridge to lasso. Now, I'll talk about this parameter and what it's for in a couple of minutes. We'll need to rerun the logistic regression, and as this will change the inputs into the stack, we'll need to retrain our stack. Once we rerun, we can see that matters have improved considerably. The logistic regression AUC has increased from 0.591 to 0.703, and the stack has improved from 0.693 to 0.704. When we look at the confusion matrix, we can see that the logistic regression is not just simply picking repairs. Now, the purpose of this video is to discuss stacking, not regularization or hyperparameter tuning, but I don't want the change that we just made to our logistic regression model to be mysterious. Regularization simply means constraining the model, and this is done to avoid overfitting to the training data and help the model generalize to perform better on data that it has not seen. For a logistic regression model made up of weights, we can constrain our model by not allowing the weights to get too large. During training, we can penalize bigger weights by adding a term to our cost function that penalizes large weight multipliers. LASSO stands for least absolute shrinkage and selection operation, and the formula is shown on your screen. When compared to ridge regularization, you can see that the key difference is LASSO penalizes large absolute weights, whereas ridge penalizes large squared weights. This has the effect of driving the weights for the least significant features for LASSO close to 0. As regards getting the best generalization out of your models, regularization is a crucial topic, but for the purposes of this video on stacking, it's less important. So don't worry if regularization is unclear. I'll do a future video series on the topic. So to finish the video on stacking, let's just quickly select another couple of models for our aggregator. Thus far, we've used logistic regression, the standard default. Let's see if support vector machines or neural networks offer any improvement. To do this, we'll drag the neural network model into our canvas, and instead of it being an input learner to the stack, it's our aggregator. With 1 output neuron and 7 input neurons, we'll opt for a single hidden layer of 4 neurons. This does not improve our performance from the logistic regression aggregator. While we might be able to tweak the parameters of our neural network to get a better outcome, this video is really about illustrating the concepts behind stacking. So to conclude, let's just add one more model, this time a support vector machine. Again, we can drag the model in and hook it up to the aggregator slot on the stack. At the end of this training run, we neither improve on the performance of the neural network or the logistic regression model as the voting aggregator for our stack. So based on this evidence, we'd stick with the default logistic regression aggregator. So in summary, stacking is yet another powerful ensemble technique to enhance the performance of AI and machine learning systems. Here we let a bunch of diversified models come up with their individual predictions. We then feed these predictions into an aggregator model and train that to be able to combine the prediction information to achieve a better outcome. We do this by breaking our sample data set into 3. The first set is used to train the base models. The second set is used to train the stack aggregator using the predictions from the base models as inputs. And the final set is used to test the aggregator. This is Richard Walker from Lucidate. Many thanks for watching. This concludes our short video series on ensemble techniques. To see more explainer videos on AI, machine learning, Web3, DeFi, and data visualization, please visit lucidate.co.uk/forum or follow Lucidate on LinkedIn at linkedin.com/company/lucidate-limited. For more information, use any of the links on your screen.